Hi, welcome to another edition of Calculus 3. Today we are going to talk about partial derivatives. Let's go ahead and start with the review of derivatives from Calculus 1. So, you remember in Calculus 1, if you had the function y equal to f of x, we showed its derivative by f prime or df dx. And the important property of it was that it was a slope of the tangent line to the graph of the function y equal to f of x. So if this is the graph, when I find the tangent line to it, the slope of that is what the derivative specifies. Now when we are going to higher dimensions, instead of a curve we have a surface, and then we want to define a slope for it. But again, as before, we noticed that we have a lot more room for maneuver and movement in a space, and therefore the concept of a slope is going to be a bit more specialized. So what we have here, suppose I have a surface like a mountain, and say I'm at this point on the mountain, I'm thinking about how to climb it. Well, I can be ambitious and try to go for the peak, shortest possible route that I can find, or I can take my time and perhaps go at some reasonable angle and go up in that direction. So we have the concept of directional derivative when it comes to space. If I have a surface like this blue surface here, so this is z is equal to f of x and y, the graph of it looks like a surface. If I want to define a directional derivative, it means, well, choose a point, choose a derivative like this vector u, build a plane right on top of this point in this vector, and let this plane slice your surface. Okay, so the surface could look like anything. After you slice it, you're back in the situation of calculus 1, that you have a curve that's the where you are slicing the surface. Okay, on that curve you can go ahead and find the derivative or the slope of the tangent line. So what you find there depends on the direction that you have taken, and that's going to be called the directional derivative. We are going to come back to this topic later on in this chapter, but I think that's a natural place to start the topic of partial derivatives. Let me go ahead and show you this in the context of a nice graphics made by one of our colleagues. So here is a graph produced by Dr. Alfredo Alberca. So what we have here is some surface. That's the graph of the function that you want to type in here. You can go ahead and type whatever you want in this place, and you will have its surface shown here. A point is chosen. A point, for example, a point with coordinate 1, 1. You can change it by changing these two sliders. The point 1, 1 is this point P at this location. Then you can choose a direction. The direction is this direction of this red arrow here. It at certain angle, you can go ahead and change that angle as you like. So for example, the angle now is set at, say, 54 degrees, whatever it is. Well, on top of this vector, right at this point, we construct a plane. This green plane is our slicing plane. The slicing plane cuts the surface, so it's going to cut it on this parabola that you see here all the way to the other side. If we go on this parabola and find the slope of tangent line at the location, we are finding a derivative, and derivative is shown by f prime of u. So the derivative in the direction of u. Okay, so that's a directional derivative. Again, we are going to come back to this topic, which is typically in the middle of the chapter, but I think it's better to see it up front. Now, if I go change this angle, suppose I go and reduce this angle, let's see what happens. My plane is going to turn. Suppose I go all the way towards 0 degrees. So at the very beginning, I have the 0 degrees. So 0 degree, I have this slicing plane that is parallel to the XZ plane. When we have that particular situation, that when this vector is parallel to the x-axis, the slice we get and then find the slope of the tangent line on it, we call that partial derivative with respect to x. With respect to x, it means that I am moving in direction of x. There is no movement at all with respect to direction y, because we have chosen to be perpendicular to it, and then we are moving in x direction. Now let's go play this game. Suppose I want to make a partial derivative with respect to y. So what do you think should be the angle that I am going to cut the plane at, that's the surface at? So what do you think? I keep going. I want to slice parallel to the y-axis, parallel to y-z-axis. So I keep going. At what angle do you think I should stop? Of course, if you say 90 degrees, you had the right guess, except that my hand is not okay. Right, 90 degrees. So this plane now is slicing our surface, and it's parallel to the y-z axis. The slope of the tangent line I find here is called partial derivative of f with respect to y. So again, with respect to y means y is the variable, y is changing, I'm moving in direction of y-axis. How about x? Well, no, my x is fixed. If I am on this slicing plane, my x is fixed, and it's just a certain number. What number is it? Well, whatever the x you have chosen here, that's what your x is at. So that is the content of this lecture, really. So let's go ahead, take a look at the situation. Suppose I want to define what is f with respect to x. Let's go ahead and write an example so that we have a specific formula to work with. Suppose I have f equal to, it doesn't matter what function I write here, but let's say, suppose I have x squared plus say xy plus say y squared. Now the graph of it would not be like this, but this is just for illustration purposes. So what does it mean to write f sub x? F sub x, so that means that cut your plane with cut your surface with a plane that is parallel to the x z axis. Excuse me, with respect to xz plane. So this is my slicing plane that's parallel to these. When I slice my surface, I get, say, this green curve. On that green curve, I choose this particular point. At that point, I find the slope of the tangent line there. So if I'm here in my formula and I want to do the same thing, I should remember that my y is a constant, because when I am on this red plane, my y is a fixed quantity. So if y is a constant, then the derivative of y squared will be 0, derivative of y will be 0, and so on. So if I want to take a derivative of this, when we say with respect to x, so derivative of x squared, just as in calculus 1, is 2x. Derivative of x y, you have to keep remembering that y is a fixed quantity, like a 5 or 10 or radical 2 or something. So if it's a fixed quantity, derivative of x y, what would it be? So for example, if you have 5x, the derivative would have been 5, is that right? Now if when you have yx, the derivative is just y. F sub x is one notation for this. There is another notation, which is to write this partial notation, partial of f with respect to x. Now while we are at it, let's also write f sub y, or partial of f with respect to y. I haven't drawn the picture here, but if you can imagine a plane that is parallel to the yz plane. So this is yz, the derivative with respect to y. Now x will be considered a constant, so its derivative is 0. Derivative of this x is also 0. So if I had, say, a constant 5 times y, its derivative would have been 5. Now derivative of x times y is just x. Derivative of y squared would have been, well, no different than before, it's just 2y. Let's go ahead practice this thing in a few other cases. Let's pick some function, some easy function. So suppose I have x, say x cubed plus x2y4 plus y5. What is partial of f with respect to x? Let's practice both notation. Partial of f with respect to x. So to keep it short, consider y as a fixed quantity and just differentiate with respect to x. So this becomes 3x squared, and derivative of this is 2x. This is held constant. So how about y to power 5? Well, derivative of a constant is 0. I don't need to write the 0, but just to indicate. How about taking the other derivative f with respect to y, or partial of f with respect to y? Well, remember, derivative of x cubed will be 0. X is held as a constant, so it's a y that is changing, so it's going to be 4x squared y cubed. And y to power of 5, its derivative is going to be 5 y to power of 4. Sometimes you have taken the derivative and you want to take the derivative again, so we have the following: f x x, or second derivative of f with respect to x. That simply means take another derivative of this thing with respect to x again, so that's going to be 6x from here. And how about the second one? What do you think I should write? The derivative of this thing with respect to x. Derivative of x is 1, so I just get 2y to power of 4. What if I wanted to do the same thing here? Partial of f with respect to y. Second partial of f with respect to y, or written in another way, f y y. So I take a derivative of this thing with respect to y. What would that be? So derivative 4x squared is a constant that stays here. Y cubed becomes 3y squared, so I'll have 12x squared y squared. And this one is 20y cubed. So these are the second partials with respect to the same variable. We could have mixed our derivatives. After I've taken derivative with respect to x, I can take a derivative with respect to y. So after I have derivative of something with respect to x, second round I can change my mind and say, okay, now I take a derivative with respect to y. That's how we are going to write it. And if you want to abbreviate it, is second partial of f with respect to the last one is on the left and first one is on the right. I take this thing, take a derivative with respect to y off of that one. So derivative of this will be 0. Derivative of this one will be 4y cubed times that. It becomes 8x y cubed. I could have done the same thing to the second one. That's partial of f with respect to y. After I have done that, I can take a partial with respect to x. In that case, the way this is going to be written is x was the last and y was the first. So if I take a derivative of this thing with respect to x, derivative of y4 is 0. Derivative of x squared is going to be 2x, and we'll have 8xy cubed. You notice this is same as that. This is not a coincidence. In fact, for category of smooth functions, the functions where these second partials are continuous in a disk, is that they turn out to be the same thing. That is Claro's theorem. So pretty much all the functions that we know that we work with have this property that these two turn out to be the same. You're probably going to prove that in your advanced calculus class, but right now we just state it. So if my function is such that its second partial derivatives, these two, turned out to be continuous inside of a disk, then they will end up being actually equal to each other. As a matter of writing, if I want to write this thing with a partial notation, we have to do f sub x first. So if I want to write this thing, if I use this notation, x is first and then y came later. So that's how it's going to be written. And in this case, f y is first and then x is written last. But as we said, we don't need to be all that careful here in this course, because every function we encounter, these two mixed partial derivatives are going to be the same. Okay, so this section is going to be very nice and simple, unlike the previous one. So let's go ahead and do a few exercises on this topic, and we'll be ready for more advanced issues. Until next meeting, good luck and God bless.